Hey guys! Alright, today we're going to do Chapter 6, Section 4, which is natural logarithms. So you'll notice that the first thing we talk about is the compound interest formula, which you should remember from advanced algebra. It's a equals p times 1 plus r over n to the nt, where p is your principal, that's the amount that you actually put into your investment, so your initial investment. R is your interest rate, make sure it's in a decimal. N is the number of times that you compound your interest per year. T is the time in years, and A is the amount after T years. So first thing you're going to do is complete the table on your notes just by assuming that P is 1, R is 100%, aka R is 1, T is 1, and you're just plugging all that stuff in with your different N values. And you should notice after you do all that, if you haven't done that yet, go ahead and pause the video so you can take a minute. Okay, what you should notice is your first value is 2, your second value is 2.61, your third value is 2.714, your third value is 2.718, and the last one is 2.718. So it's getting closer and closer and closer to that 2.718 value the more and more that you compound. So basically what that means is that as you are compounding more and more, you're compounding more and more continuously, okay, you're getting closer and closer to that 2.718 value, which just so happens to be E. So this E value, that's equal to 2.718 something, okay? It keeps going. It's an irrational number just like pi. So pi is equal to 3.1457 blah, blah, blah. It keeps going. Okay, E is the same way. It continues on infinitely, and it's an irrational number. Okay, so we use E to represent this number 2.718 that your compounding function approaches as you compound more and more and more. So this leads us to our continuous change model, which I like to call the PERT formula. It says if a quantity P grows or decays continuously at an annual rate R, the amount A sub T after T years is given by A of T equals PE to the RT. So that's your principal investment times E taken to the interest rate times the time as your exponent. Okay, so A of T equals PE to the RT. And that's what you use whenever you have interest that is going to be compounded continuously. So if it says it's compounded monthly or yearly, you use your original compound interest formula, which is that P times 1 plus R over N to the NT. Okay, that's your normal interest compounding formula. If it says compounding continuously, that means that you have to use the PERT formula. Okay, so anytime you see that compounding continuously, that means use PERT. All right, we've also got this thing called annual yield. We're not going to talk about that very much, but basically you just need to know that if you compound continuously, you can get the annual yield by using the formula e to the r minus 1. Okay, so e to the r minus 1 gives you that annual yield if you compound continuously. And if you're not sure how to do problems like that, there is an example in the book. I believe it's example 1. Okay, so we've got a problem here. We've got two investment plans. They both have an interest rate of 8.275%. One compounds daily, the other compounds continuously. We're investing $5,000 for 10 years. We want to figure out how much more interest we're going to get from the plan that actually compounds continuously. So essentially what we want to do is we want to figure out how much we're actually getting out of each of those plans, and then we can compare them and find the difference. So if I start with my plan that compounds daily, I know that means I'm going to be using this formula, okay? And if I just think about what my variables are here, I know that P, that's my principal investment. So in this case, that's going to be $5,000 because that's what I'm putting in. R, that's my interest rate, so it's 8.275%, so that's going to be 0.08275. Okay, I've also got the number of years, so that's T. T is 10. I also know that with this specific plan, I'm going to be compounding daily. So remember that N is the number of times I compound per year, so daily would be 365. Okay, so now I can plug all this stuff into this formula here. So I can say my A is going to be 5,000 times 1 plus 0.08275 over 365 to the 365 times 10. Okay, now what I can do is actually plug that into my calculator. So I've got my calculator right here, and I'm going to start with the stuff in parentheses. So I'm going to say 1 plus, in parentheses, I want to have 0.08275 divided by 365. Okay, and I get 1.000226712. You're going to take that answer to the 365 times 10 power. Make sure that's in parentheses also. That gives me 2.287, etc., etc. I'm going to take that answer times 5,000, and I get $11,436.89. Okay, so that's how much my daily interest compounded formula gives me. Now remember, I'm comparing it to something that's compounded continuously, and if something's compounded continuously, I need to use my PERT formula. So now I'm going to use my PERT formula, and I'm going to use the same values over here, except in this one I don't need my N because I'm compounded continuously. So I've got 5,000 times e to the 0.08275 times 10. Okay, so I can just plug that into my calculator. I've got 5,000. That e button, if you look at your calculator, there's that natural log ln. Okay, if you do second ln, that'll give you e to the whatever power. So you'll hit that, and then you'll type in 0.08275 times 10, and we get 11,437.96. Okay, so that's how much I make if I compound continuously. So notice that if I compound continuously, that's going to make more money than if I compound daily. Now I need to figure out what the difference between them is. So how much more money am I making? So I'm just going to take this one, and I'm going to subtract out this one. So in my calculator, if I do 11,437.96 minus 11,436.89, you'll notice that you get a difference of $1.07. Okay, so $1.07 over 10 years, not bad. All right, so why do we even care about this E thing? Well, this E is really useful when you're doing interest formulas, which hopefully you realize is actually pretty relevant, especially in the accounting industry and things like that. Okay, mortgage industry, all that stuff. So remember that we've already talked about inverses between logarithms and exponents. We know logarithms and exponents are inverses of each other. Okay, so I know that y equals 10 to the x and y equals log base 10 of x are inverses. So how do I find an inverse? Well, an inverse, remember, is when you swap the x and y values and then you solve for the y, the dependent variable, sorry. Okay, so I swap my x and y values and I solve for my dependent variable. So generally that means solve for y. So if you want to find an inverse, okay, let's say I'm finding the inverse of y equals 10 to the x. Okay, what you can do is you can start by swapping the x and y. So you get x equals 10 to the y. Now the problem is if I want to solve this for y, well, I don't really know how to do that unless I use a log. So I can rewrite this in logarithm form, and I'll have log base 10 of x equals y. So this and this are inverses of each other. Okay? So we can do the same thing when we have a function with e as a base. So if I have e as a base, so like y equals e to the x, if I want to find the inverse of that, that's where your natural logarithm comes in. So a natural logarithm is basically just a logarithm with a base of e. So this one is your common log. It's got a base of 10. This one is going to give you your natural log. So if I want to find the inverse of this one, I'm going to swap my x and y. Then I can solve for y by taking my logarithm. And if you have log base e of x, that is the same thing as the natural log of x. So this is the inverse of y equals e to the x. Okay, so remember that e is important for compounding, and we can find the natural log, which is just a logarithm with a base of e. There's nothing different about the natural log except for the fact that it specifically has a base of e. All right.